thing about drone batteries. Unmanned aerial systems have remade entire industries in less than a decade. Carbon fiber frames slice through wind with improbable efficiency. Flight controllers make thousands of micro adjustments per second. Artificial intelligence assists with navigation, obstacle avoidance, mapping, and cinematography. The aircraft have evolved at a breathtaking pace. But the thing about the batteries that drones use is they have not. What I am about to tell you will likely frighten you, and it should. So, imagine 5 high-capacity lithium polymer batteries stored improperly. They are no longer just power sources for a drone, but a concentrated reservoir of chemical energy totaling over a megajoule, capable of initiating a severe thermal event. If a single cell fails, it can trigger a cascading reaction across the stack, creating a self-sustaining chemical fire that reaches temperatures exceeding 1000 degrees Fahrenheit and vents hazardous vapors. This intense heat is capable of compromising structural materials and spreading rapidly through a residence, effectively turning a simple storage oversight into a high-speed industrial-grade fire. Understanding the immense thermal mass within these high-density cells is critical, as treating them with anything less than rigorous safety protocols ignores their potential to cause significant property destruction and life-threatening conditions within minutes. Think about the potential danger to life and property, the financial liability. For all the advancements overhead, modern drone flight is still chained to a chemistry that hasn't fundamentally changed in years. Lithium polymer and lithium-ion cells power nearly every commercial drone in the sky. They are compact, energy-dense, and capable of delivering astonishing bursts of power. They are also the weakest link in the entire system. The core problem is weight. In aviation, weight is not an inconvenience. It is an adversary. Engineers speak of energy density, the amount of energy stored per kilogram. Current lithium batteries hover around 250 watt-hours per kilogram. That number may sound abstract, but for a flying machine it represents a wall. Add battery mass and you add lift requirements. Add lift requirements and the motors draw more current. More current means more heat and faster depletion. Eventually, adding battery capacity does not extend flight time. It shortens it. This is the quiet paradox at the center of drone engineering. The thing that keeps the aircraft in the air is also what holds it back. Ground-based electric vehicles can tolerate inefficiency. Add more batteries and the car simply weighs more. The road is not affected by the added weight, but in the sky, that added weight means everything. For a multi-rotor aircraft, lift is a continuous negotiation with gravity. Every additional gram must justify its existence. Until energy density undergoes a radical shift, solid-state chemistry, hydrogen fuel cells, or something not yet commercialized, endurance will remain constrained not by software brilliance, but by physics. If weight is the engineering limit, chemistry is the safety limit. Drone batteries are not mild-mannered power banks. They are high-discharge systems, built to release enormous amounts of current instantly. A heavy lift, a rapid climb, sudden correction against wind. These maneuvers demand violent bursts of energy from cells that are already operating near their thresholds. When this system collapses, a domino effect can take place, turning your hobbyist tool or your business appliance into an uncontrollable destructive force. Energy becomes heat. In high-temperature environments, batteries struggle to shed it. Internal pressure rises. Cells swell, a phenomenon operators casually call puffing, though there is nothing casual about what it signifies. In cold environments, the chemistry slows. Voltage drops under load. The battery may report a comfortable remaining percentage, yet be physically incapable of sustaining the amperage required to keep the motors spinning. A drone that takes off at 80% can descend at 30, not because the charge disappeared, but because the voltage collapsed. The sky offers little forgiveness for chemical hesitation. Then there is time. Unlike many components of a drone, batteries age whether they are used or not. The degradation clock starts at manufacture. Every charge cycle increases internal resistance. Every high current discharge accelerates structural fatigue within the cell. In practical terms, most high-energy drone batteries remain trustworthy somewhere between 200 and 400 cycles. After that, reliability becomes uncertain. And uncertainty in aviation is unacceptable. Ownership adds another layer of discipline. A fully charged lithium battery does not like to remain full. Leave it at 100% for days and the stress increases capacity loss and swelling risk. Leave it depleted and it may drop below recoverable voltage, effectively killing itself. Operators learn to discharge batteries to a narrow storage voltage window after use, neither too full nor too empty, as if maintaining a chemical truce. Few technologies demand such vigilance from their users. Fewer still combine that vigilance with the consequence of gravitational failure. The irony is stark. Drones appear futuristic, autonomous, almost casual in their capability, but their power source remains temperamental, finite, and chemically volatile. The aircraft can stabilize against wind gusts, avoid obstacles with machine learning, and return home automatically. The battery cannot negotiate with thermodynamics. And so every flight becomes an exercise in restraint. Responsible operators monitor cell balance, temperature, discharge rate, and cycle count. They consider ambient temperature before launch. They land conservatively, never trusting the optimistic final percentages displayed on screens. They treat batteries not as accessories, but as critical flight components, because that is what they are. The public imagination gravitates toward propellers, cameras, and autonomy. The real constraint, and the real risk, is quieter. It sits in the belly of the aircraft, humming with stored potential. Drone innovation will continue. Frames will get lighter, controllers smarter, sensors sharper, but until energy storage breaks through its current chemical ceiling, flight time will remain rationed, and safety will remain tightly bound to a volatile balance of weight, heat, and degradation. The thing about drone batteries is not that they fail often, it's that they are always operating at the edge, and in aviation, the edge is everything. Take care of your drone batteries, take care of yourself.